All right. Good. Well, happy Thursday, everybody. So last time we introduced a new set of tools from the sample-based motion planning. And more generally, I wanted to start motivating this idea that there really are a bunch of other tools out there inspired more from sort of AI-style search and a little less from optimization. And the sample-based motion planning was the first set we looked at. But today I want to spend some time trying to make maybe some more substantial connections between the optimization world and the search world for you. In particular, I want to keep thinking about, do we have a satisfying solution to this problem, right? So, flying around obstacles, but also with interesting underactuated dynamics, right? So this is a beautiful problem in the sense that it has kind of this combinatorial aspect of it, of trying to decide, am I going to go left or right around each of the trees? But it also has the continuous dynamics of the quadrotor, right? And the sample-based planning that we talked about last time, I really think it requires some additional tools from dynamics and control to make it effective for underactuated systems. I think the closest I gave you to a solution last time was from Emilio's thesis about using the value iteration to solve for the cost to go of the unconstrained problem, and then using that as a way to guide the search for a sample-based planner of the constrained once you put obstacles in. And that is a fairly satisfying solution. But I still think, you could sort of say that's maybe pretty specific to this plant where we could just barely do value iteration. We found a way to sort of make that work. It's funny, every time I teach, right, I go back through my old notes, I read all the new papers, but when I go through my old notes for the sample-based planning, I always have something to myself like, there's got to be a better way. there's got to be like a clearer way to think about this, because for me, they've been incredibly effective, but they're so heuristic that our current understanding, I think, of when those work, I think the probabilistic completeness sort of story is clean, but then the nuances that make one algorithm better or worse than another feel very heuristic still, right? And there's got to be something better, right? And I don't claim to have all the answers for you today, but I think we're beginning to sort of peel back and understand some of the deeper connections, I think, between trajectory optimization, which is very good at the continuous dynamics, sample-based planning, which is very good at deciding to go left or right around the tree, but then you're going to take these sort of straight line trajectories, and you have to do more work to potentially bring the dynamics in. And is there some way to connect the two? Okay, so there's a line of work that we're working on right now that I think just telling you this story in a few of the pieces of this story, I think is my goal for today, is to try to tell you how we can actually solve that trajectory optimization, that the quadrotor flying around dense forests with convex optimization now, which sounds too good to be true, right? We've been saying the whole time that going left or right around the tree, that's these collision avoidance constraints are sort of the biggest source of non-convexity that you can easily point to, and it's been my working example. So how can we possibly use convex optimization to solve a problem like that? And the answer is going to come sort of in three parts. Okay, so the first part is that we have this nonlinear dynamics of the quadrotor, and we've been saying these nonlinear underactuated dynamics, these cause you to have nonlinear, non-convex trajectory optimization problems. So I think the first question is sort of, how do you make trajectory optimization for the nonlinear plant look convex that's the dynamics question. And to preview the answer, there's a class of underactuated systems, an important class, where you can actually change variables into a different coordinate system, where you can solve convex optimizations to solve this. And the name of that approach is differential flatness. Some of you will have seen it before. Differential flatness. For systems that we can find a differentially flat coordinate system, we can change a potentially very hard trajectory optimization problem into an easier one, with some caveats that we'll talk through. Okay. The second question, the second reason why that problem should feel non-convex is that, how do you make these collision avoidance constraints? Look more convex. And the answer to that one is going to be you don't quite, but you can do something that's pretty good. You can turn these problems into a union over convex sets. Okay, so which is something you saw a bit in the footstep planning, where you have to decide, I'm going to be in this set, or this set, or this set, or this set, right? So we can make it at least into the union over convex sets for many collision avoidance kind of problems. And then, there's going to be, for instance, mixed integer formulations for that. Which is related to these disjunctive programming. If I say I'm in set A or set B or set C, then that's a disjunctive optimization. Yes?
What exactly do you mean by mixed integer?
Good. So you'll see plenty of examples. That's part of this is the preview with words that will be explained throughout the lecture. But I think there's three different ideas that I want to communicate, and I want to just give the palette, sort of the high-level story here. Okay? And then the third one is this, there really is the combinatorial problem of left or right around the tree, right? So what chance do we have of figuring out this sort of combinatorial problem, which is related to this union, okay? And it turns out this one's going to have a very satisfying solution, okay? There are examples of combinatorial optimization using convex optimization. And we're going to introduce a few, one of those, we're going to connect to some, convex combinatorial optimization. In particular, look at the shortest path problem on a graph. It's going to be the relevant workhorse for us. Okay. So it turns out there's a set of ideas that if you put them together, allow us to actually solve those really hard motion planning problems with some caveats. I'll be super clear about them, using convex optimization. And time will tell whether these approaches are going to be the ones that everybody wants to use for their quadrilateral. I think there's open questions there, but I think at the very least it's another piece of the puzzle of trying to understand how all of these tools connect. Okay. I actually part of the reason I wanted to put up the the overview like this is I actually want to start at the bottom because that's the one that's most dissimilar to what we've seen before. And if you only remember one thing, I want you to remember this one. Okay? So let me start with talking about shortest paths on a graph. Okay, so it's a very famous problem. It's sort of, you'd find it in a convex optimization text. You'd find it in a combinatorial optimization text. But the problem of shortest path, often called the shortest path problem, often called abbreviated SPP, on a graph. Okay, so this would be a directed graph, if you like, even. So I've got some directed graph. I'm going to make an arbitrary cartoon here, but okay, so it'll be a weighted graph. I can have costs associated with taking a particular edge. Okay, and the problem will be if I identify some node in the graph as my source, another node as my target. How do I find a path, a shortest path that takes the minimum cost trajectory from the start to the goal? Okay. Now there's loads of algorithms for this. Computer science loves to study these, right? There's Dijkstra's algorithm, A-star, all kinds of good graph search algorithms. Okay, but I'm going to tell you how to do it with optimization, with convex optimization, independent of whether it's going to be the best algorithm for this problem. It's going to make the intellectual connections that we want to make it push further. Okay, so I'm going to define this as having vertices, which I'll just denote by an integer I, okay. Edges, which are described by a tuple of vertices, a direct, that live in some set E. My costs, I'll call Cij for the cost of edge ij. Okay, and then I'll have my source vertexes, source S and target T. Okay, so my goal is to try to write an optimization-based solution to that totally reasonable problem. Here's the basic prescription. I'm going to use as my decision variables. We always call them phi for a variable. I would like it to be, well, let me just call it like this first. This is associated with edge ij. In particular, I want, at the solution, I'd like it to be true that phi ij is 1 if ij is in the shortest path. And 0 otherwise. Okay, that's my goal, is to write an optimization that has that property. That at the optimal solution, I'm going to read off the shortest path by looking at the edge variables. Okay, now the objective, given that goal, it could be easy to sort of understand. I can just say, if I want to minimize over all my decision variables, right, the sum of Cij, Vij, and this is just the sum of all the edges that are in the shortest path, right? So that is the path length. And it's linear in the decision variables, right? It's a linear objective. Because those are constants. Those are just given to me as the problem specification, right? Now, to make this true, I really want these edges to either be completely in the path or completely out of the path. I'd like to say that all of my phis are either 0 or 1. This is an integer constraint. And since I have both integer constraints and continuous constraints, or integer variables here and continuous constraints, in general, I'm going to think about this as a mixed integer optimization problem. This one is actually just integer optimization problem, but okay, and now I need to something that sort of denotes the connectivity of the graph. Like, I haven't put anything in here yet that tells me, am I allowed to, something about where are edges, where are not edges, and somehow I need the graph connectivity to come in. And the way we're going to do it is with something called flow constraints. And the flow constraints look like this. What I'm going to say is that for all vertices I, I'd like to say if I sum over the edges coming out of that node, all of the phis, it better equal the sum of all the binaries of the edges coming in to that node. Okay, so let's just think about what that means. So if phi can only be 0 or 1, I'd like at the optimal solution for some shortest path, I'd like that at every node, I've got some number of edges coming in, I've got some number of edges coming out. For it to be a valid shortest path, I expect only one of these to be active coming in, or 0. It can be 1 or 0. If I have at least one, if I have one coming in, then I'll have one coming out. Okay, otherwise it had better be 0. But certainly the number coming in has to equal number coming out. I listed a bunch of different artifacts, right? Like, if all of these are 0, then these would all be 0. If exactly, if one of these is 1, then one of these is 1. It turns out all of those details are captured just in that one sum constraint. Right? The sum coming in equals the sum coming out. The sum could be 0, the sum could be 1. We'll find out in the optimal solutions, that's true. Okay, and we can generalize this a little bit. In fact, there's a special case, which is the source, where you don't actually need any coming in. You just want to be able to have one coming out. And there's another special case, which is the target, where you're allowed to have one more coming in and none coming out. Okay, so the slight generalization that you'll see in the books of this would be written like this: Ij plus equals where this is This is a delta function, which is, this thing takes values 1 when t equals I and 0 otherwise. Okay. So if it's the target, I automatically get a fake 1 coming out that I don't have to use. If it's the source, I get it arbitrarily. I get an extra 1 coming in. Yes?
Would this ever break if there were two equivalent shortest paths leading into a node?
That's exactly the right question. So the question was, what if there's multiple paths of exactly the same length, right? More generally, it could go through one node. It could even be 2 paths around the tree that are exactly the same. That's exactly the right question to ask, and let's revisit that in just a second. Yeah. Okay. So it turns out that that's enough. If I write down those problems and solve this program to optimality, then this will solve the shortest path problem. Okay. Now, okay, maybe I should go ahead and answer your question right away. So what happens in the case of there's, for instance, 2 equally good paths? Okay, so 1, 1, 1, 1. That's the edge costs. You could imagine, if you didn't have that integer constraint, you could imagine that it would try to split and make phi equal 0.5, 0.5, for instance. That would be a fractional solution. Okay. Right now, as I've written it, that integer constraint is going to force it to pick, right? And the way that you solve these integer problems, it will actually just check them all, and so it could tell you actually that both of them are optimal. Okay, so this is going to be robust to that. Also, cycles and all these other things, all the details actually work out if you work it through. This will be so give you the right shortest path. Now, this question becomes more pressing when I tell you that actually, if I write the same thing, if we do the convex relaxation of this, this is a convex objective. It's a linear objective. This is a linear constraint, a quality constraint. So that's a linear constraint. That's still convex. It's only this thing that is causing non-convexity, right? Because my solution has to be either 0 or 1, and 2 points between that solution, 0.5 is not, if the constraint was convex, it must have the property that if I have a feasible point, 2 feasible points, then every combination of those feasible, affine combinations of those feasible points would also be in the set. That's not true for this explicitly. It's, 0.5 is not in that set. The convex relaxation of this would be to relax phi ij is either 0 or 1 to just saying phi ij is between 0 and 1. Yes?
Which constraint is enforcing the source and the target to be connected? So why can't it just set all edges to 0?
Because it has to set, that's a good question, that's a great question. So why can't it set all edges to 0? So it's still happening here. So because the target, for instance, has automatically a 1 coming out, that means that at least one of these has to be 1. And the chain of implications there takes it all the way through to saying that you must find some path which satisfies the constraints, and then you try to find the minimal one. Yes, that's great. That's exactly the right question. Okay, so what happens if you relax this 0 or 1 constraint to saying, let me search for any problem at any flow variables between 0 and 1. Okay, that's the natural convex relaxation of this integer constraint. It turns out, key result, the convex relaxation is still tight. What does that mean? That means if you solve the convex relaxation, you just solve this version of the problem, then we know, and I'll give you an intuition about it, but I won't give you the full proof. But we know actually that if you just solve the linear program, it will always return a solution if you solve the linear program using a proper linear programming solver, like a simplex method or something. It will always return variables that are either 0 or 1. And that solution is actually, because it's integer feasible, actually gives you the global optimal solution. Okay? In fact, it turns out even just asking for phi ij greater than or equal to 0, you don't even need the 1. It's already enough. The 1 is redundant.
Why won't it split in the equal cost path case?
Yeah.
Why won't it just split across the two?
Yeah, good. So if I do this, the question is why won't it split? So it could assign phi equals 0.5, phi equals 0.5 all the way around, right? That would obtain an optimal cost. But the picture, we haven't talked the details. I mean, I guess Alex's tutorial on linear programming probably said this. But the picture that people use to analyze linear programs is that you have only linear constraints. Typically, the interesting ones are these half-plane constraints. Okay, and then you have a linear objective. So it is possible that the optimal solution lies anywhere on a particular face, but there's always a solution at a vertex. Okay, and with high probability, actually, it'll end up at the vertex. Okay, and a simplex method, for instance, a solver will just walk across the vertices and find the optimal vertex. Okay, the vertices in this problem, which we can actually see if we look at it for a minute, are all integer feasible. Okay, so you can that's a pretty good way to do it. So if you think about what are the constraint sets here? So this constraint set, even the relaxed version of this constraint set, if I have a bunch of variables that are between 0 and 1, that makes a big box, the hypercube. Okay, in some high dimensional space, there's a cube. Okay, and then the only other thing I'm using, so already I have this shape. It's the shape of a hypercube in high dimensions, and then I have a bunch of linear cuts on that, equality constraints, and with a little bit of thinking, so if it's not the source and the target, if it's just this version, then this is a bunch of, all those variables have to go through the origin. Okay, so it will only ever intersect the hypercube at one of the existing vertices. And even when you add a 1 here, it will still only intercept the original hypercube at a place where it'll only intercept the hypercube at 0 or 1. So it doesn't change the number of, it changes the number of faces, but it doesn't introduce any new corners that would be fractional. Okay. Now I wish I had produced the proper proof for you, but it is the case that you can always find an integer feasible solution, even when fractional solutions are optimal. Okay, it's going to be this case where the entire face is equally good. So an LP solver, using simplex method, for instance, will always return the integer feasible, or if it doesn't, you can just pick one yourself. Okay, so this is it's a well-known result, but it's an amazing result. It says you can do graph search with convex optimization. Now, would you ever want to do that, right? So like if we have A star and that's a great algorithm, we have Dijkstra's, that's a really great algorithm, would you ever want to do this? This might be more expensive for any given graph than that. But like I said, just the same way, remember I introduced semi-definite programming to find the Lyapunov function for a linear system, and I was like, you would never do this. But then we generalized it to common Lyapunov functions. And it's, having put an optimization language behind it, now we're going to be able to add more constraints, more objectives connected to other tools, and still leverage the power of graph search. So in particular, let me do it a little bit out of order. Okay, so think about this problem now, where I want to find continuous curves. Okay, so I want to fly a UAV through a maze. Okay, it turns out we can solve this problem nicely with the tools we're going to talk about here. But why is that not surprising? The reason that's so if I was just solving this like in the Sunday paper, then I would think about this is just a graph. Even though it looks complicated, it's maybe hard for humans. For a computer, I could just make a graph where there's a vertex at every box and an edge if there's no wall between the boxes. So graph search should just crush this problem. It shouldn't be a hard problem. Okay, as it stands, if I were to say now turn into a problem of a UAV flying through the maze, then everything we've said is suddenly that does become NP hard. In more than 2 dimensions, it's NP hard. That's a little weird, right? Like, why did a problem that looks so easy, if I suddenly like have to find a continuous curve that fits inside it, why does that get so much harder? This is going to be the leverage to say, let's find a way to write the easy part of the problem in optimization and then throw in some of our trajectory optimization under the hood, and we'll be able to solve the continuous part of the problem pretty well with convex optimization, so that we can find now like continuous curves through big mazes, with convex optimization, with just a single solve of a second-order cone program. Okay, and this was an example where if you just change the objective, let's say from minimum distance to minimum time, it'll take a different path through the maze, for instance. Okay, so the generalization of this idea to the motion planning problem goes through an abstraction, a generalization of this, which tries to bring in this idea of continuous paths into this language of shortest path problems with optimization. And the way we think about this nowadays is using this framework called graphs of convex sets. So I want to take that thing that works well for discrete graphs and introduce some continuous variables. And the picture here is I've got my arbitrary graph and I found some shortest path on it. And we're going to make what's hopefully a not too scary modification, which is we're just going to associate with every vertex in the graph a continuous set. And because we like convex optimization, we'll make them convex sets. Okay? So every time you visit a node in the graph, you're allowed to pick one element out of the convex set. That's the formalism we're trying to build up here. Okay, so now you can imagine if for every vertex we have a convex set and we're allowed to pick a point in that convex set. And moreover, if we're allowed to have our edge lengths be a function of the continuous variables, not just the discrete variables, then you can get pretty interesting things, right? You can get the shortest path through the graph of convex sets might be this orange line, for instance. If you minimized distance, if you minimize time, you might get a different things, and we'll talk about how to put dynamics in and the like. So that's a little bit harder than what we had before, but it's close. You can imagine how the two will be connected. Okay, so here's the classic shortest path problem we just talked about. And if you now try to do the same thing with continuous variables also, then you get this formulation, okay? Cost times the binaries. This is the edge length, now a function of x times the binaries. Exact mapping, okay? Flow variables are unchanged. The flow constraint is unchanged. I mean, we added this. It turns out to be powerful enough. It's important, again, to add this less than or equal to 1, okay, which was redundant before. This is the same. We added one new set of constraints here, which is that x has to live in the convex sets. So I have new decision variables. For every vertex, I have an x. X lives in the convex set, and then I have these binaries. So this problem was convex. We've only added this convex set, but the objective is now a decision variable times another function of decision variables. So this is a bilinear objective. So just because we had we have two things that are good, like let's say we have convex optimization for trajectory optimization, we have convex optimization for the graph, you can't just magically put them together and hope everything's convex. In this case, it becomes bilinear. It turns out, though, that that's a particular form of non-convexity that we can sort of address, okay? So we go from a classic shortest path problem to the bilinear problem. Bilinear objective in particular. But it turns out when you have bilinearity multiplied by these binary variables that are between 0 and 1, that's a particular type of binary of non-convexity, or of the bilinearity we can address in a nice way. So in particular, if I have any convex set, and I have a binary variable, or even a relaxed binary variable between 0 and 1, then the set defined by the sort of multiplication of this thing is a convex set in a higher dimensions. It's called a perspective function. So if you imagine the origin and you imagine my set X, then if I multiply by this phi in this higher dimensional space, then it's going to look like the projection of this, the convex cone created by taking that convex set. When phi equals 1, it's the original convex set. When phi equals 0, it's 0. Okay? And that object, which is the perspective function, it's called, we can be more precise about these, but I think this is the right level. Okay, you can see, is still a convex set. So it turns out, even though we've got, now it's a convex objective times a binary, okay, that we're going to relax. This thing lives in 0 and 1. We can do some reformulation and massaging of this to turn this still into a, we're going to use perspective functions, and it turns it into a mixed integer convex problem. In this particular setting, we've thought a lot about the particular formulation, this sort of framework. There's also like a bunch of additional constraints that you can write these additional constraints. We call the most important one spatial flow. Which are these funny constraints that, not funny, but they're important constraints that for the mixed integer problem, they are just redundant. They don't actually add anything to the formulation. They don't change the solution to the mixed integer problem. But they have the property that when you solve the convex relaxation of the mixed integer problem, they do add strength. So they make the convex relaxation more likely to be tight. This amazing result we had for the graph problem was that the convex relaxation was tight. It's not true in general for the graph of convex set version, but we can add constraints that make it more and more true, closer to being true. Or for more problems, it turns out to be true. And you put these together, and very often, the convex relaxation is tight. Okay, so when I showed, for instance, this maze problem, there's a lot known about the Euclidean shortest path problem if you wanted to solve just even the simplest Euclidean distance problem inside a graph. We know that it's hard in 3D or above. In 2D, there's actually a polynomial time algorithm. Okay, but in 3D, there's a polynomial time epsilon approximation. In 4D, I think nothing is known. Okay, but we know that it's NP hard already in 3D. It turns out if you formulate it with this graph of convex sets, that we have a polynomial time algorithm for this, which we know there's bad instances. It doesn't make P equal NP. There are bad instances, but for every graph I think we've ever thrown at it, the convex relaxation is tight. And same thing for the UAVs. We've built statistically a bunch of warehouses, for instance, randomized maps, and we just run the statistics and say how often is the convex relaxation tight, and the answer is it's very often tight. And when it's not tight, there's a small gap, and there's a simple sort of rounding strategy which makes it even more likely to be tight. Okay, but the reason that works is because we're leveraging the graph structure, which makes this problem easy. Yes?
Can you define what you mean by tight a little bit more formally?
Yep. So there's in mixed integer optimization, which I haven't defined super formally, but you did have a problem set on it, so I got to lean on that. We're going to compare the optimal solution or the optimal cost from the original problem, the mixed integer problem, versus the convex relaxation. And we ask what's the gap between the solution of the relaxed problem and the original problem. It's tight when the gap is 0, and it's stronger as the gap becomes 0. There's a whole language sort of in these mixed integer optimizations where you talk about the strength of your relaxation. And the stronger relaxation or the tighter relaxation will have a smaller gap between the relaxed problem and the original problem. Yeah? What this means is statistically we can almost always get the optimal solution by just solving the convex version of the problem. Yes?
Well, what are the assumptions about the loss L here, like other than convex?
Convex is the assumption. I mean, so in fact, the way I wrote it, we didn't allow also constraints between there. You're allowed, L is allowed to go to infinity, obtain infinite value at finite x's. So it's really convexity is the assumption. Okay, yeah. So for a large class of problems now, we can we can write this sort of leverage this shortest path problem on graphs and try to connect it to trajectory optimization. I haven't gone all the way to connecting it to trajectory optimization yet. Hopefully by the end of the lecture I will. But let's go to the next part where I'm going to try to tell you a little bit about how we get to address the nonlinear dynamics and make that trajectory optimization for a UAV be convex. Yeah? Will people walk away at least remembering the shortest path on the discrete graph? Yes? LP formulation of SPP? It's a good thing to know. Okay, let's talk about differential flatness. So the answer was differential flatness. Let me just do it directly in an example. Imagine I have my planar quadrotor. The equations of motion, it's worth writing it down since they're simple and we need the algebra for me to convince you, I think. It's just 3 equations. Okay, so we've talked about underactuated in a bunch of different ways. This is an underactuated system. It has 3 state variables and 2 control inputs, right? There's a lesson that we've sort of picked up a few times throughout the term that, roughly speaking, if you have 2 actuators, then you can completely control 2 degrees of freedom. You just can't completely control all 3 degrees of freedom. Differential flatness takes that observation and thinks about it in reverse. Okay? It turns out that if you tell me exactly what happens in 2 of my degrees of freedom, if you give me a trajectory in 2 degrees of freedom, if you can find this differentially flat property, okay, for systems that are differentially flat, if you give me 2 variables, that might actually imply what my actuators must have done in order to make those 2 variables go through some trajectory. That implies something about the actuators, which then implies something about the other variables. So, right, so if you have m actuators in n degrees of freedom, you can often control at least m of them. Similarly, if you know exactly what the trajectories that happened of your robot in m degrees of freedom, for some systems that we can find this flatness property, it actually implies what your actuators must have been doing, which therefore fully specifies the trajectory that you've executed, because you didn't have any more control authority. Okay? A trajectory in m flat coordinates may, if we find the property, imply what you must have been doing, which implies all n degrees of freedom. So let me spell that out in this example, okay? So it turns out if you give me a completely differentiable trajectory, if you give me x of t, z of t, that's defined for all t in some interval, and it has to be differentiable. So in this case, for this example, it has to be differentiable 4 times. Then my claim is if you tell me what x and z was for this, that will allow me, if you tell me the quadrotor flew around and the center of mass did this thing, I can back out what the props must have been doing, and therefore I can tell you what the theta must have been doing. And you can see that algebraically. So the way to see it here, if I were to write with a simple manipulation of those equations, if I just massage these equations a little bit, then it turns out if you tell me what x of t is for all times, that means you've also told me what x dot is and what x double dot is. That implies for all t what theta must have been uniquely. Okay. Similarly, you can figure out what theta dot must have been, theta double dot must have been, and then you can plug theta double dot in here and figure out everything, as long as you have this defined differentiably up to 4 variables. So the general form of that, the differential flatness idea, it's not true for all systems, but it's true for a lot of interesting systems. If you can find some coordinates which are defined as a function of x and u, and possibly the derivatives of u, potentially arbitrary derivatives of u, such that you can write x as some function of just z and its derivatives. And u as a function of z and its derivatives. Then we say the system is differentially flat. Maybe even say the outputs, we call these in outputs Z. Right, so the way you convince me that a system is differentially flat is that you produce this change of variables Z. The one I produced up here was I said that x and z, those two variables were my flat outputs, and I could reconstruct what x must have been and what u must have been given just a functions of z and its derivatives. So a bunch of interesting systems have this. Snake locomotion, sometimes, depending how you model the snake, has it. But if you think about it almost like a train with wheels, it has it. Airplanes can have this in certain form. And famously, even 3D quadrotors have it. So there was a great line of work by Vijay Kumar and his students doing super aggressive flights with quadrotors. And one of the key insights there was that you can program very complicated maneuvers like this, including flight through windows, using convex optimization, which I'll finish making that point in a second, because the 3D quadrotors are flat. So if you've seen that work was based on differential flatness of the 3D quadrotors. And I think I wrote the derivation in the notes. Okay? So why is it that having a flat coordinate system makes trajectory optimization easy, makes it convex? Okay? If you have these flat variables, then you don't have any more dynamic constraints. So trajectory optimization reduces to just find me a z. And the way people will find a z of t is you'll just parameterize z of t, for instance, as a piecewise polynomial. Which is linear in the coefficients and differentiable at least however many times. And then you can write constraints on z, saying like z should be inside the window at time, if you say z14, z at t14 should be inside the window. Okay, if the window constraint is a convex constraint, then that implies a convex constraint on alpha. And trajectory optimization, given convex constraints on z, is convex. So in that video, it looks, it might look like they were trying to decide whether to go through the window or not. They were not. They were saying at a particular time I had to be inside the window, and they were designing trajectories that it was sort of like picking the mode schedule. You can make the problem easier if you say I'm definitely going to go inside the window at this time, right? And they'd fly up and hit that and fly back, but they were able to solve that so fast with a convex optimization that they could even move the window around, throw a hula hoop, do real-time estimation of where the hula hoop was, for instance, and dart through it. I think that was later in this video. Maybe this is the hula. Oh, here's the hula hoop. That's pretty good, right? Yeah. So they can solve the planning problem so fast that they can just throw the hula hoop up. It's in motion capture, so they're tracking the hula hoop, plan a trajectory on the fly, and dart through the hula hoop. It's pretty good. Okay, so that's piece 2, this notion that, definitely take that off. Okay, go this way so it's nice. That's piece 2. So for some trajectory optimization problems, through a change of variables, you can actually make the problem convex. Okay. There's a few things you can't do here. So if, for instance, your function that defines u as a function of z is some complex function, which it is for the quadrotors, it's actually very hard in the differentially flat optimization to put torque limits on your quadrotor. So a lot of these, luckily quadrotors have almost no torque limits, and they can do very aggressive things. But one problem with the differential flatness is that you can't make the problem convex if you have strict torque limits that define your motion. Okay, but for very aggressive maneuvers, this is a pretty successful approach. Questions about that? Yes?
Is there a standard way to write down adjust variable?
That's a great question. So I would love to give you like a numerical recipe. So the question is roughly, is there like a recipe? If I give you x dot equals f of xu, can I give you an algorithm or something that would find these change of variables? I don't know of one. I don't know that it can't exist, but I don't think there's any known recipe. Right now, it's still like let's say the Lyapunov functions were a while ago, where you just had to be clever and come up with one. I don't even know how to check if a flat coordinates exist, which could be a slightly easier problem. I don't know that. I know that I have not seen that, and I would have noticed if I saw it. There's people that have thought a lot more about it that might know why it's hard or have leads on it. But yeah, I think right now it's still, when somebody discovers for a particular system that the system's flat, they write a paper, everybody starts using it. That's what happened in the quadrotor case. Things leaped forward when someone wrote the flat coordinates. Okay, so that was two pieces. So we had a combinatorial optimization that happened to be convex because we used this shortest path problem relaxation. We have trajectory optimization, which looked terrifyingly non-convex, but through the flat coordinates for quadrotors, we can make it convex. The last one, though, is, like I said, flying through the window, it had to say, I'm going to go through that window at a particular time. So how can we make obstacle avoidance, which feels like horribly non-convex, look more convex? It's the last piece. Okay, so let's say I have an airplane flying, right, and I want to not hit this obstacle. If I'm willing to set ahead of time the mode sequence, then I can break this space up into a bunch of convex regions, especially in the case of polygonal obstacles. Right? There's a convex region here. There's another convex region here. There's another one for every face. If I'm outside the face, being outside that obstacle is actually a convex set. Right? Of course, it gets more complicated if I have to be outside multiple regions, but actually, if you take the product of these sets with the sets that you get from there, then you can still have a convex decomposition of the space. Okay? So you can't make them convex, but you can say, I'd like x of t to be in the union of convex sets. Is sort of a reasonable approximation. It's a reasonable approximation for polygonal obstacles. Okay, if you have round obstacles, you make me sad. But you can imagine making an arbitrarily close approximation. You can do an outer approximation if you want to make sure you don't hit the pole, the round pole. Okay, but this is sort of the strategy. Is let's break up the space into a bunch of convex regions, and then ask, just like in the footstep problem that you just did, say at every time step, I'd like to be inside at least one of these convex regions. Okay, now there's a few tools that will sort of help us think about that. So the problem that is actually convex, if you set the schedule of where you're supposed to be, for instance, so let's say I have convex sets xi. If you were to say, just like we did with our hybrid trajectory optimization, if you were to say, let's say like x at time 0, x at time 1, x at time 2, we're all in x0, and then I'm going to say, x of time 2, x of time 3. I'm going to say all of these are in x1, and so on. This would be, this is sort of like having a mode sequence. Then this problem is convex. So if I've decided to go left or right around the pole, then I can make that convex. The hard part is saying I don't know if at time 4 I'm going to be over here or I'm going to be over here. That's where you get a disjunctive program, this or this. It turns out there's a transcription of this problem into that graph of convex sets. Okay? It's going to use one more feature, which is that I can place entire trajectories inside a region. If I'm in a region here and I have entire line segment inside this region, then I know because this set is convex and this line is is convex, that I could say these 2 points being inside this region means the entire trajectory is inside the region. That's a nice feature. It turns out there's ways with correct spline parameterizations to say that if this entire, with a few checks on this curve, I can say that this entire polynomial spline segment is inside this region. Okay, so here's the transcription of a motion planning problem into the graph of convex sets. Okay, we start with the red being an obstacle, the blue being a decomposition of the free space. Okay, we've got a start and a goal. We parameterize little trajectories. Well, first we make the graph, I guess, so which is to, if any two of these regions connect, if they have any overlapping space, which in this case is just, the line is the intersection, then we're going to make an edge in our graph of convex sets. So I have a discrete graph sitting on top of this, like the maze problem. And then in every one of the regions, I'm going to make a little spline that can be a polynomial up to arbitrary degree. And I'm going to say it's completely contained in here using my spline properties to be inside this set. And then I'm going to write constraints on the edges of my graph of convex sets, saying that if this edge is inside the shortest path, then additional constraints hold. For instance, this point and this point must be connected, and the trajectories have continuous derivatives, and you can write lots of extra additional constraints like that. Okay? So that as a solution, all of these other constraints are not in the shortest path. They effectively get turned off by the binary variables, and the final trajectory is here. Okay, so that's the complete transcription then, roughly, with a lot of math behind it to make it work. That turns this sort of motion planning problem around obstacles into a problem that you can write as a graph of convex sets, which is a mixed integer optimization. And what's surprising is that even for quad rotors and hard problems, the convex relaxation is almost always tight. Okay, so a couple fun examples. David and Mark were generating random environments, random mazes with trees and rooms and windows that you had to fly through. Okay, and statistically, it's very close to being giving the optimal solution almost always. What's cool is it also works for harder problems, like if you have to build regions. If you have to do this sort of convex decomposition even in configuration space, so you're doing it in joint coordinates instead of in 3D coordinates, then we're still able to find convex optimization solutions to what would be classically hard motion planning problems using this sort of graph of convex sets. Compared to the PRM type approaches, the trajectories here are, when the convex relaxation is tight, it actually gives it, and we can certify it just by solving the convex problem. We get globally optimal trajectories. The PRM does not give globally optimal trajectories. It goes all over the place. People do a lot of post-processing with the PRMs to try to clean up this trajectory. A shortcutting is a standard approach to sort of clean up the messy trajectories you get out of PRM afterwards. And that does a lot better, but in high dimensions, the graph of convex sets can be considerably better solutions and even solved in less time. I say that with a qualifier that some people have highly optimized their PRM implementations, and we have not highly optimized ours yet. This one's really exciting for me because this is 14 degrees of freedom. Remember we said that PRM tops out at about 10 degrees of freedom is about the most I've ever seen it. This is 14 degrees of freedom with pretty complicated collision avoidance constraints, right? And it's being solved to global optimality with the convex optimization. Okay. A big part of that is figuring out how to do this convex decomposition automatically in these hard configuration spaces. Alex actually has a nice paper on that, on how do you write a sums of squares program in order to solve for these convex regions. But the picture I want you to have in your head is roughly like this. So we solve these optimization problems by finding a seed and trying to blow up with semi-definite programming, roughly very large regions of configuration space. So in the PRM setting, I said you got to start in a goal, and the way we're going to do it is we're going to sample, and we're going to start building a graph, whatever, right, in the PRM setting. What the vision is for this graph of convex sets problem in hard spaces is that every time you draw a sample, instead of just making a point that you can connect to, we're going to immediately blow out the biggest possible approximate convex set in that region. I'll grab another point. If I've already got it inside this region, I'll reject it. I'll grab another point, have another big automatically discovered convex region, right? Grab another point, and with a pretty quick but approximate convex segmentation of the world, you can do pretty interesting things. There's an algorithm called Iris that does this nicely in 3D, and Alex extended it to the general case of joint coordinates, which is much harder. And you get decompositions that look like this. So you start with some bounding volume, and then instead of drawing the PRM like we did, we just start sampling and make the convex sets inside the region and draw edges across those convex sets, and then we write this convex optimization that stays inside the sets. And this is where you can start to see the potential gaps, right? So just like there's a only, the PRM is only probabilistically complete, we have some probability of eventually sampling all of the open spaces. It's not probability 1, it's only probabilistically. And there are some other gaps in terms of the way we contain a polynomial inside each convex region. It leaves a little bit of a gap, and we're super careful in the paper to sort of talk through all those gaps. But once we have the convex decomposition, the class of polynomials that we search over, we solve to global optimality. Anyhow, so that's a cool thing that I'm excited about right now that we're working hard on. What I like about it is, I think it's a good solution to the problems that we're trying, like these 14-dimensional arms. But I really think for me it connected a few dots in my head that were disconnected for years. Like my old notes kept saying there's got to be a way to think about this trajectory optimization and sample-based planning a little bit more similarly, right? And I think there's a lot more work to go in this vein. For instance, in graph search, people solve like really big graph search problems by using strong heuristics, right? And like if you're doing Google Maps to drive from here to San Francisco, right? There's an incredible map of all the streets in the world that most of them are not entered into the solver's head in order to find the path from Boston to San Francisco. You're only adding exactly the roads that are necessary sort of on your path, or plus a little bit of the boundary, right? Because of these strong heuristic-based searches and incremental planning. Right now, to solve the graph of convex sets, we decompose the entire world. We load the entire graph with all of its optimization problems into the solver, and we one time say, here, solver, do your best with it. And I think there's a much more I think the connections that we want to leverage from the discrete combinatorial search into this problem will help us, write trajectory optimization type problems that are more incremental in nature and that scale to much bigger problems and can have some of the task level discreteness inside of it. Yeah, what else? Yes?
So this works in most cases? Are there cases where it works poorly?
Great question. So when does it work and not work? So I think we've identified the key places where some of the key examples. So we certainly have a reduction to show that the problem is NP hard. So we know that there are instances, we've given instances where it's definitely hard. There's even problems that we would like to solve well that it doesn't solve well in the paper. But actually, a lot of times the metrics that the cases we know are hard are not the problems we tend to want to solve in motion planning. So for instance, if you have a shortest path problem, then that tends to encourage the solver to visit only a small number of nodes, and that's a place where the convex relaxation is often tight. The reduction we make to NP hardness is actually the Hamiltonian path problem, which tries to visit all of the nodes. And you can choose cost functions that will, try to take a tour effectively of the graph, and those are the NP hard ones. So we have a statistical argument for motion planning problems, and we have some concrete examples of hard problems, of places where the relaxation is not tight. The exciting thing, though, is that even when the relaxation is not tight, we don't have a theorem saying epsilon optimal, but even when the convex relaxation is not tight, it tends to be close. Like if you were to take that solution and run it, you'd only be like a small percentage worse than optimal. Yeah.
Can you go back to the previous slide?
I started going all over the place, so I don't know which one's previous. This one?
No, like the one where you get the convex regions.
Okay. Yeah. This one?
Yeah. Yeah. So I have a question. So assume that we are doing this in configuration space.
Yes.
And for this to work, like we actually need to have this plot of every obstacle, right?
Good.
Like
yes.
Instead of doing it in RT or probably zero map, instead of just doing checking, here you need what you need is more demanding. You need to generate those obstacles. How is this done in configuration space?
Awesome question. So the question is, I would maybe summarize the question as how does it connect to perception, for instance, like or dynamic obstacles or anything, like if the environment's. So for robots where they're operating in a known environment, I think you can just, you can make your CAD models, you can compute your regions once, you're good. But if someone walks into my space, for instance, what do I do? Is that a fair summary of your question, or?
Actually not exactly.
Okay.
I think my question is more about configuration space.
Okay.
Do you, or as you say, if you have perception, you have the CAD models. Do you do sampling to put those dots there, or do you explicitly?
He's asking how you build the obstacles in C-space.
Yeah.
Okay. So so in C-space, the picture is basically the same, except for so in this problem, we assume that the obstacles are convex, or we make little convex decompositions of the obstacles. In configuration space, first of all, the obstacles are just not convex because even if you had a convex body on your arm, if you start moving it through the nonlinear coordinates, you get very curvy, shaped boundaries. So you have to inner approximate these curvy boundaries, which is why some of the sums of squares tools were a better fit than fitting half-plane kind of things. Although we still use half-planes. But the other thing is that you want to avoid trying to explicitly compute the configuration space obstacles, right? So we basically write a small optimization that says, find me the biggest regions, subject that no point, or there's different ways to spell it, but basically that no point inside this region is inside this region, even when you move through different joints. There's a nonlinear optimization that's easy to understand for that, and then there's a sums of squares optimization that's more sophisticated to do that work. So you do have to solve an optimization problem to find the big configuration space free regions, but you don't have to necessarily explicitly compute the exact configuration configuration space obstacles.
But you still need some kind of constraint from the obstacle, to draw those lines, right?
As long as you know what the geometries are in 3D, then you can work with those geometries plus the kinematic equations in order to understand the constraints that are imposed on your free space. You never have to make the geometry in Q space, okay. The obstacle geometry in Q space. You try to make the free space geometry in Q space that bumps up against the implicit constraints of moving those through kinematic coordinates. Yes?
How feasible would it be to extend this to the case where the drone could only observe finite horizon in front of it?
Yeah, exactly. So that's the one that I thought people were going to ask, right? Was what if you have perception, right? So I think there's two. There's a couple ideas. So I think even a probabilistic roadmap type idea, you would typically make a big roadmap, pre-compute a big roadmap, And then if you had new obstacles that come in, you would trim your edges, right? And you would prune your tree and then plan with that pruned tree. And I think there's got to be an analogous, we haven't worked it out yet, but that's the next thing we'll try to do. I think there's an analogous thing where you have I'll take some time with my bimanual manipulator to avoid all those self-collisions. And then if I drive up to a new table, I will shrink those regions in order to avoid collisions with the new runtime constraints, right? So that's the way I would imagine initially trying to connect it to perception. But that's to be worked out. Yeah?
When you're automatically generating these regions, like in this approach, how do you then go into the mode sequencing part of it? Is it sort of, you've got to stop and then get someone in the loop to pick the times and pick the points, or?
Thank you for asking that. So the question was, how do I go on to the mode sequencing? So instead of giving a specific mode sequence, I'm going to write it as a graph of convex sets and allow the shortest path machinery to choose the mode sequence. That sounds like it should be a hard problem, but we're leveraging the shortest path relaxation being tight in order to make that decision for us. So it is not a preordained mode schedule in this one. This one is solving for the mode schedule and the trajectory simultaneously, and it's still tight. So this is and we're trying to push this all the way back to hybrid planning. I think it's a better way to write the hybrid planning problem too. Yes?
I think to follow up to Boyuan's question, so I think, so in those plots you were showing, was it like a 2D robot with like two joint angles? Is that what we can think of it as in the future? And now the obstacles have to be brought into like joint space, right?
That's a simple version of it, but we've got it working even in 14 joints.
Okay, yeah. But
Yeah.
I guess the question, maybe this was his question as well, is it like, I guess the most naive way of representing the obstacles in joint space is you could like sample a bunch of joints, check it with
Yep.
a collision checker, and now you have points, right?
Yep.
But what is the data structure? Is there something more than just like sample-based representation of the obstacles, or is there like a data structure or shape or something?
Beautiful. So we are not, so the question is, are we sort of sampling, for instance, in configuration space in order to build up a configuration space obstacle? I could totally see why I gave that impression with the picture I just showed, but that was for when we were trying to do collision avoidance against perception, like a point cloud. For the joint space obstacles, we actually just take an analytic form, spheres, boxes, cylinders, whatever, for the geometry of the arm. We take the algebraic kinematics, and we can do exact certification. So we have two versions. We have a nonlinear optimization SNOPed version that's super fast, but doesn't give strict guarantees of non-collisions. It does very well. We use that often, actually. And then Alex has a sums of squares version that is certified, that actually takes the algebraic equations of all those boxes and everything and guarantees that you're not in collision. And if you're in an environment where you have a little bit of time to pre-compute those things, then that's going to, it's worth a few minutes of computation in order to solve those exactly and have those rigorous guarantees.
And those black boxes were visualizations of those?
I combined, that was an animation I like, but this is actually the old version of Iris. So this is not the configuration space. This was saying these were supposed to be a dense set of trees, and actually we were trying to show that original algorithm scaled to even thousands of obstacles. But this is not representative of what we're doing in the configuration space obstacles. Those are swept volumes of simple geometries through the algebraic kinematics. Yeah. Cool, I appreciate the questions. Anybody else have any questions? One administrative thing, so we are going to do the face-to-face check-ins, the project check-ins. They're expected that all groups should do a check-in. We're trying to make sure that you've, are making progress. If you're making good progress, use it as a chance to tell us what your. I think Lou's posted some, explicit sort of recommendations for how you can spend your time. If you're making good progress, then ask us like, how do you make Drake do this, or how do you, I'm totally happy with that. Our goal is mostly to understand that you're well on your way and making progress on the problem. If you're having more fundamental questions about how to formulate the problem or whatever, we're happy to talk about those things too. But we'll put some specific instructions up, and there's a scheduling sheet that's up, just been posted, that has a bunch of times tomorrow, a bunch of times Monday. If those don't work, let us know, but I'm hoping we can make those work. Okay, see you.